So we couldn't have a DevOps conference without a dedicated Docker talk. Next up, we have Tim here to tell us more about how he's using Docker for IoT. Tim Perry is a senior software engineer at Resin.io. He has experience in taking teams and customers from the initial idea to eventually the final release. A frequent speaker in international conferences, article author, and open source enthusiast, and lots of much other stuff. Here is Tim. Now it works. One fast survey in the DevOps world, you can have usually two typical backgrounds, from a software engineer or an operations infrastructure engineer. Can we see how we stack up here? So who's from a software background? Okay, and from infrastructure background? So actually there are more people from a software engineer background. Nice. Okay, Tim, you have the stage.
Okay. Good afternoon, everybody. I want to talk to you about Docker. Docker is a powerful, exciting tool. It solves a lot of interesting DevOps problems that we come up with again and again and again. So Docker also creates some problems of its own, though. Like any shiny new tool, it gives us some solutions and some new interesting challenges. Today, I want to look at how we use Docker at Resin to build a platform for IoT, some of the problems we come up with there and some of the interesting solutions that you find along the way, and particularly how multi-stage builds let us solve some of the thorniest parts of this, both in IoT and if you're using Docker anywhere else. Let's start with some context. I work for Resin. We're a platform for people developing IoT devices. So we allow you to git push your code to us, we build it in Docker, deploy it to devices, and then allow you to remotely manage and reconfigure and use these devices. So if you've got 5 or 10 or 10,000 Raspberry Pis, you can easily set them up, write code, push it, and not worry about the rest of the details. This is the goal here. When I talk about devices, I'm talking about things like this. So everything from the Raspberry Pi up in the top left to the Pi Zero down in the bottom. This costs $5. This is a working Linux machine that fits in the palm of your hand easily and is going to be cheaper than the shipping for the device. The Intel NUC in the middle is an x86 Intel machine, much closer to devices you might be used to day to day, but on a smaller form factor and using much less power. And then we've got things like the TX2 down in the bottom, in the center. This is built by NVIDIA, a graphics card manufacturer, built for high-performance parallel processing and doing complex machine learning and AI in an embedded system in the field, doing machine learning embedded into physical devices somewhere. We're trying to get all of these working and try and ensure that you can easily write code for any of these out of the box. IoT is an interesting new place for all of this kind of stuff. It's fascinating. There's been lots of interesting talks today about different aspects of it. It's full of problems. Loads of stuff doesn't quite work yet. And unlike DevOps in a lot of other scenarios, there's no clear consensus on what the right answer is for almost anything. Most problems you'll come up with building applications elsewhere, there's at least some consensus on what a good idea, a good solution normally looks like. And that simply doesn't exist in IoT. There's no clear answer to how you should typically architect an IoT application. Nobody knows what good IoT UX looks like. How you deal with failure in IoT is a A totally open question. And particularly, what I want to look at today is how you deploy and manage and monitor IoT applications. How you actually do practical day-to-day DevOps of a production environment of tiny machines out there in the world, somewhere that you can't reach. This is an interesting problem because it's similar to DevOps that you might be used to in a cloud environment in many ways. And our goals are very similar, but the actual solutions you have to come up with end up being very different. So in a traditional cloud environment, you might be used to the idea of thinking of servers as cattle instead of pets. They're not things to be carefully taken care of and managed. They're things that you should carefully set up once, organize a reproducible process for, and then if they ever break, throw it away, get a new one, and ensure that your process allows you to do that. Allows you to quickly scale up and spawn new devices, and allows you to throw away broken devices. That's great, and that's very useful, and in IoT, you cannot solve that problem by doing that. A lot of your devices are doing important things. They might be in a car, driving the car. You cannot throw that away if it breaks. It's busy. You need to be able to get these same solutions, solve these same problems, but with a different approach along the way. Our solution to a lot of the key problems here is Docker. So Docker's obviously very popular in a cloud environment. Everybody, I suspect, almost everybody will have heard of Docker, if not actually used it. But in an IoT environment, you get even more out of it. So, in a cloud environment, perhaps, you get value out of isolation in Docker. The ability to write one service, put it on a machine, and then write another, put it on there, and control the possible ways in which they can interact is a really useful tool for managing your production environment and knowing exactly how everything works. That is an important, useful thing in IoT as well. But even more, isolation allows you to actually practically do development. It's really easy for IoT applications to become closely entwined with the OS itself. These are typically not just a web server responding to requests, they're also directly talking to attached circuitry, attached bits of hardware. They're directly managing drivers and firmware. They're often managing the network connection of the device. The kind of thing that your code in a Docker container in a data center is not typically doing. And if you're doing all of that, it's very easy for your code and the OS to become a kind of blurry line. A lot of your application is tied closely into OS configuration. As soon as you do that, updating the application becomes very difficult. It's tied into the OS, and you effectively have to update everything together, which is an incredibly dangerous thing to do in a device you can't touch. If you update the OS and the application all at once, and it goes wrong once, ever, your device is bricked. You cannot update it again. You can't reach it to go and reset it. You're completely stuck. Being able to separate the OS and the application so you can update the OS independently allows you to do that much more safely. And that isolation from the OS gives us a lot of tools to make that work. Reproducibility, again, is very useful in a data center. The idea you can run something in a Docker container on your machine, put it on a server, run it there, and have it do the same thing is great. It allows you to go really quickly, it allows you to trust in what your production environment will do. And in IoT, that's also great, but even more important, you may have heard that security in IoT is a difficult and messy problem in a lot of ways. Being able to ensure that when a security issue comes up, you can come up with a fix and put it into production, knowing exactly what it's going to do, has enormous value for resolving these issues. And finally, application delivery. This, in the web world, if anything, is actually quite simple. A lot of the time, you just need to put code on your server and start it. If you put an FTP server on your web server and you copy code into there, you can make that work. You can get by with something like this. In IoT, that is a complete non-starter. A lot of your devices are not accessible. You often can't connect to them, or you've got slow or expensive connections to get there. They need to be pulling updates to themselves. They need to be doing so efficiently, and they need to be, as much as possible, in careful control of when that happens, so they can manage and ensure that updates only happen over Wi-Fi, but not cellular connections, for example. All of this doesn't work with simple tools, but Docker gives us tools to do this really easily. A Docker pull is a quite efficient, practical tool for pulling software onto a device to update it. And we get all of this out of the box with Docker. So this gives us a really good base for IoT development. All of this put together gives you an architecture that looks something like this. We have a user on the left who Git pushes code to our cloud services. We accept their code, we build in servers in the cloud. We've got native ARM servers so that we can build specifically for ARM devices. We then host a Docker registry which stores our users' Docker images. On the device, meanwhile, we're running Docker. And a supervisor, which is a Docker container that talks back to our API and works out what the device is supposed to be doing. It should be running this image, it's currently not. So it uses Docker to do a pull the latest image from the registry, update to that, and then it reports status back through the API and through to a UI and a CLI. So there's a web management interface that allows you to see what your fleet is doing. All of this is not that far from a classic DevOps approach, a classic architecture you might have for building and managing software elsewhere. You build code, you deploy it to servers, and then you get statuses back out. Unfortunately, though, IoT is very new and still comes with a lot of problems that do not come up in this kind of classic environment. So, for example, your production environment often is literally in users' hands. It's devices that are running in their homes, in their cars, somewhere out in the street. It is devices where anybody can walk up to them, pull out the SD card, and have a look at the hard disk of your production environment. They're devices where people will mess around with them in all sorts of ways, and they're often running on untrusted networks as well. You can't trust any of the other things around you that you might be talking to. We need to build a secure platform despite all of this. And particularly the code itself. It's very easy, especially with Docker, to end up with your entire build process and any secrets required during a build process embedded in the resulting image, which you then put out into production and put into the hands of anybody who walks past. You also have problems with reliability. A lot of users are running devices that don't have reliable power. This is the kind of thing that doesn't come up in a data center. You've probably got pretty reliable power and backup power. Often for IoT devices, you have somebody wandering past and plugging it in because they want to use it and just pulling the power out when they're done. And you have to make things work on environments. You have things running on cellular connections or no connections where they intermittently get connectivity. This is a green sea turtle. It's an endangered species. They're about 1.5 meters long. This is swimming in the ocean off the west coast of Africa. Attached to its back is a Raspberry Pi Zero running Docker and Resin and a camera. This results in some fascinating footage and allows you to track and understand these animals. How do you deploy software to the turtle? This is an interesting problem. You do not have reliable network, it's running on a battery. You do not have reliable power. You can update it and recharge it when it comes in to nest on the beach, eventually. Building software that you can effectively manage in production environments that look like this is a hard problem. So, we built a few things that have allowed us to start making some progress here. Firstly, we've built an OS, Resin OS. This is free and open source, so you can start using this for yourself if you'd like. It consists of a minimal lightweight OS built specifically for IoT with Docker pre-installed, pre-configured, and ready to go. It's got support for 25 or so boards, all of the Raspberry Pis for starters, but then things like Odroid, BeagleBone, lots of the Arctics. It comes with pre-configured support for lots of modems, networking, popular hardware that our users use, and is pre-secured, so you don't have to think about trying to secure your OS configuration in these kind of difficult environments where you can't trust everything around you. And then on top of that, it's actually read-only. The root partition of the file system is not changeable. It is fixed when you install a specific version of the OS. And by doing that, we guarantee that even with unreliable power and with things like SD cards as our disks, we limit corruption to the minimum possible. Nothing on the normal file system changes. And there's a separate part of the file system that is mutable and is managed with AUFS, which is we found to be the most reliable option for this kind of thing, for limiting the risk here. But this isn't quite enough. So we also built our own Docker engine called Balena. This is built on top of the Moby framework, so it's using the same internals as Docker, with some extra changes we've made on top. It's fully Docker compatible, so the API is the same and the command line is the same, but improved in a bunch of ways for IoT use cases. So it's 3.5 times smaller. We've dropped a few features that you don't need in IoT, things like overlay, networking, and swarm. We've also carefully tweaked the build process to shrink down the binary as much as possible. Also improves Docker pulls. So normally, when you pull an image with Docker, you pull all of the layers that have changed. So base images that haven't changed, for example, you don't have to pull, but any layer that has changed at all, you pull completely. And this is simple and effective, but potentially very expensive. So we do that same process, layer by layer, but then we pull diffs for each layer. And this means in real-world use cases, like an apt-get, where you install lots of packages, if you add one package to it, that doesn't invalidate the entire layer. You only pull the diff of the new package you've added, rather than breaking the cache of that whole layer. And that's these enormous improvements in the amount of data you have to transfer over the air, at the cost of a bit of extra complexity. It's particularly built for low memory environments, so we make some different trade-offs, slowing down pull performance a little bit in return for ensuring we don't thrash the disk, and we can guarantee very low memory usage throughout pulls. And we work a lot on atomicity and durability to ensure that even if somebody pulls out the power halfway through, either you get a whole working image or you don't. And you don't end up with corrupted pulls and updates that will break devices. And all of this is great and gives us an architecture that looks something like this. We have an OS, including Balena, we've got a supervisor, and then the user runs a set of containers doing whatever they like on top of that. And we give them a framework that lets you do lots of this security and reliability stuff for you. It gives you a good base to solve some of these problems. And that, sadly, is still not quite enough. There's only so much we can do on the device level. If you keep pushing 2 GB updates to the turtle, you are going to have a big problem successfully getting those to go through in time, successfully updating software, and successfully getting everything out. And we need to ensure that users, before the images get to the device, have all the tools they need to be able to effectively manage IoT software. There's 2 really key questions we're left with here. How do we actually build fundamentally smaller images? Not just deliver them better, not just improve the reliability of pulls, but make them actually smaller from day one before we even start optimizing that? And how do we hide build secrets completely? We don't want to make it difficult to get into the server. We want to make it difficult to get any information even once you do. And generally, how do we keep stuff out of our images? And this is something that Docker doesn't really help you do. By default, you just keep running commands, your images keep building up, and then at some point your image is done, and you put it into production, with all the history and process behind it that came with it. This is interesting because this is especially important in IoT, but it's important if you're using Docker anywhere. You probably don't have people with direct access to your production servers, directly reading your hard disk. But you could. Being able to ensure that even if an attacker manages to get into that position, they do not steal the raw source code of all of your services and all the build secrets required along the way is a valuable thing. Being able to ensure that you have security despite that risk is a useful thing, even if you're running in a cloud environment. Similarly, for image size, if you're pushing 2 GB images every day, even on a good network connection, that is going to cause you constant little bits of pain. Just managing disk space on your CI servers as you keep running these builds becomes a hassle. You can't just pass somebody an image to quickly reproduce something. If your Docker images are 50 megabytes, that's a much, much simpler, easier process. And you gain a lot of power and agility in your development process if you can have smaller images. So, let's start talking practical. This is a typical Docker file you might see, which has some problems. So we start off with a base node image. We take a build argument for the npm token, and we log in with this, and we're going to use this to install private npm modules. So you see a similar pattern anywhere where you depend on some kind of private repository for code. We then create a folder that our code's going to live in, we copy in the code, and install dependencies, build the code, and then clean up our npm login. And then we say, when you start this container, you should run the resulting single-built JavaScript file. This is how you might write a JavaScript application and build it with Docker. This has some problems. Firstly, this, with an empty project with no dependencies, is 700 megabytes. If you're on an intermittent 2G connection, you do not want to pull 700 megabytes. You will not complete that this week or this month. And it will be extremely frustrating trying to build on top of this. We also end up with some security issues. So here we insert the token to log in, and then we try and remove it later. But this doesn't work. What we end up with is history between these two stages that leaks this information. So we can take a Docker image built with this Docker file, and you can use the Docker image inspect to get all sorts of interesting metadata about that image. One of the bits of this is that for each layer, you can see the actual diff from that layer, the actual files that were changed or created. If you take this path from that upper dir section, and you actually just go and have a look at it, you can read the root/npm rc file in there, and you can directly read the token out of that, even though later in the build process it was deleted. So if you've got the image, you can go and look in the layers and pull out that information. Even if you couldn't do that, it's also available in the history. Anything that turns up in a build argument lives in the history of the image. You can do Docker history image and see every step that image has been through since it was scratch, since it was a blank, empty image. All of this leaks information into your production environment. And anybody who can get access to your production environment can do exactly this and get every bit of code or arguments that you added to your image at any point. There's a few classic solutions. Combining run commands for a long time was a recommended practice for Docker. So instead of logging in and then later deleting the authentication token, you do all of this in one single run command, which means there's no intermediate layer, which means there's no layer to go and look at and see the diff. Unfortunately, this doesn't really work. You have a whole set of problems. Firstly, combining everything into one run command is extremely painful for caching. It means either that layer is cached or nothing is cached, and you reinstall all your dependencies and you rebuild everything from scratch. It doesn't help with non-run commands. If you've got to copy in code, you can't combine that with a run, and you just have to do them separately. And it doesn't actually erase the history. Even if you can't see the individual layers, you can still see things like build arguments in the history there. Another option, Squash. This is a relatively new feature for Docker. I think it came in start of last year. This allows you to squash down all the layers of your build process into one at the end. So you end up with one layer that you've built. This resulting layer has only the final changes, overall changes, combining together diffs. So intermediate states disappear. That's great, but again, it doesn't work. Firstly, you need to run the entire Docker daemon in experimental mode, which is probably not what you want to do in production. It's not declarative in any way, so you can't say in a Docker file, this file should be squashed. You have to remember to squash every single time you build anything. And if you ever forget, you will silently build a much too large image, which is leaking all your secrets, without any warning or notification. You just have to remember to squash all the time. It's actually less efficient in some cases. As I mentioned before, only changed layers get transferred in a Docker pull. If you squash down to one layer, that layer always changes. So you always repull everything. And finally, it doesn't actually erase the history. We squash layers, but we don't squash the history. So build arguments, again, are still visible. Okay, third time lucky, the builder pattern. So here, things get a bit more complicated. We take that one node Docker file we had before, and we rename it to dockerfile.build. And this is going to define our build environment. We then build that file. So we do that same build we had before, and extract files from it with Docker CP. So this lets you say, I want to take the resulting image of this build, and I want to pull out one file from it and put it on my local file system. Then we have a production Docker file, as here on the right. And this defines your production environment separately from your build environment. And this is the key difference here. We've split production and runtime, we've split build and runtime entirely into two separate Docker files. And in that production environment, you can use a much smaller base image, and and you can copy in only exactly the files you need and nothing else. And this does work. This will give you a history that only shows the steps on the right, and layers that only show the content on the right, which is the minimum you can do. Only the content you're actually going to have in production. But again, it has a bunch of downsides. So here, you'll find that this is quite complicated. Just managing a whole extra Docker file is an extra bit of hassle, and you end up writing automation around this, or just having manual steps to do this. And that gets more and more complicated as you have more and more files that you're individually transferring between these steps. And because that's complicated, people don't use it. You have a build Docker file which builds all your code and has all your dependencies, so people just run that instead. And that works great at development, and then you go to production, and suddenly you're running in a different environment to what you've been testing for 6 months, and nothing works. And you end up encouraging users away from good practice by doing this. So this is closer, but we still have some problems. This is where multi-stage builds come in. This is a new Docker feature that gives us a lot of power to solve exactly these problems in a much more flexible and declarative way. Critically, multi-stage builds build multiple stages, which hopefully might be obvious, and allow you to explicitly say how content moves between stages. So these are individual separate builds in one Docker file that pull content from one to another. What that looks like in practice is that you can go from base image repeatedly. And each time you do, it starts a separate stage. So normally in Docker you have one from at the top that says where you're starting off, and here you can do that over and over again. That looks something like this. We start off with the latest node image, we run a series of steps, and then we go to the node Alpine image. And as long as all the steps above were successful, our build uses that exact image, none of the content from before, and continues and runs some different steps. This by itself is not very useful. It gets useful when we start connecting stages together. So the easiest way you can do that is like this. You give stages a name. So here we call our first stage. When that build completes, if it's successful, we run the second stage, which uses a totally different base image, totally different content, independently does whatever it likes. If that's successful, we then reset to the end of first stage and continue from where we left off. So you can kind of pause and resume build processes here, picking up content and continuing with it later. And you can also copy content. So here, we build from base, and then we reset to this different base2 image, and we pull across one file, A. Everything else is left behind. History, layers, other files. We pull through an individual file using this new --from option. This is especially interesting because --from you can now also use in single stage builds. You can go --from any image identifier and pull individual files from that. You can say you can use a node 8 base image and say from node 9 pull one individual file, and that will be pulled from Docker Hub or wherever, an individual file extracted, pulled into your build, and it will continue. So you can extract individual bits of content from other images elsewhere. All of this gives you separate stages where the history of each stage and the layers in each stage are independent, which allows you to really precisely control what ends up in the final stage that we're working with. And the final stage here in that file, the last one there, is the default end result. So if you're thinking about looking at the ID that you have at the end of your build, or if you're using --tag to tag the result of your build, that last image is what you're going to be using. You can override this. There's a target option that you can use to build only the build stage or a test stage or something like this, but that's the default. This allows us to do interesting things like test stages that get reset. So here, we start with a build stage. We build our actual code. You compile everything that you're going to use at runtime. And then we have a separate stage that continues from the first one, from build stage, and installs some extra things, perhaps Selenium and a web browser, things that you only need for testing and that you definitely don't want to put into production. You install all of these, you use these, you do your testing, and as long as it passes, you continue to the last line, which is from build stage, which resets back to the end of build stage. Throws away everything that happened in your test stage completely. It doesn't exist in your history, it doesn't exist in your layers, all that content instantly disappears. And this allows you to start building interesting graphs of different stages where you pass content back and forth and you reset and throw things away and carefully control what ends up in your final images. There's a couple of things to watch out for here. Non-target stages, so by default everything except the end stage, are considered dangling, which means if you ever do Docker system prune, they all just get deleted and you wipe all your caches, which will be unexpected and potentially quite annoying. This also doesn't work with cache from. Does anybody know what cache from is? Okay, I've given this talk 3 times, and so far one person has known what cache from is. Okay, so cache from allows you to do some slightly obscure behavior where you pull an image from somewhere else and use that as your cache, which is typically useful if you're building in different places. So in our particular case, we build in the cloud normally, but sometimes you build on a device. And it's really useful to be able to use the previous cloud build as a cache for the build on a device. And cache from lets you do that, and if you do it with multi-stage builds, it breaks all your caching, which defeats a lot of the point. Putting all of this together, we end up with a Docker file that looks like this. And this fixes our node problem. We start with that same node image, node-based image, but now we give it a name. We call it build. And then, towards the end of our build, we start a new, fresh stage. We throw away everything before, and we use an Alpine image, a much slimmer image that perhaps doesn't have everything we need for our building and development processes. And then we copy in just the one file from the previous stage that we need, and then we start everything else up as normal. And all put together, this lets you effectively implement that builder pattern we saw before, but directly and declaratively in a single Docker file. So you just run docker build, and this just works. And content gets copied back and forth, and we end up with small and relatively secure images. This takes your 700 megabyte image down to 70 megabytes, which is a much more palatable size for delivering over painful network connections. This also removes it from the history. So this is the history of that image. Everything that says 5 days ago is the actual node-based image itself. So it's installing yarn and base node, and then those last 4 steps at the top are all that you're leaking from your build process. We create folders and use it as a working directory for our code. We copy in a file, and this is how you run it. No other information, and that's what we're putting out into production. This can actually go even further if you're looking at low-level languages. So things like Rust and C and Go can build static binaries, where a single binary contains all your runtime dependencies. You don't need any libraries or anything else on your system other than this one file. And if you're doing that, you can make your production deployments incredibly efficient. So here we're using a Rust builder-based image, which builds a small demo web server. It's a server you connect to, it says hello world. It's a small demo Rust application. This results in a 2.3 gigabyte image, which again is not an acceptable thing to send over a lot of network connections. Even fast connections, that is going to be painful to work with. If we start using multi-stage builds here, we can instead use from scratch. So here we give that first stage a name, and then we use from scratch to start a new stage with a completely blank image. Scratch is a Docker image that has nothing in it. And then we copy in one binary, nothing else, expose a port, and say how to start it. And this one binary is all you end up with in your image, and you've got a 5 megabyte image, which is an extremely easy to deliver thing, even in difficult environments. All of this is very exciting. It's only available in relatively new Docker. So this comes in Docker 17.05, which was released in May last year. So if you're reasonably up to date, this is available and ready to use right now, and lets you get all of these benefits very quickly and easily. To recap them, this lets you control image history, which in IoT, where we can't trust production environments, is very important, but is important for everybody else too. This allows you to ensure that even if somebody gets access to your production environments, they don't have access to your whole source code and all your build secrets and your build process along the way. This lets you control the image size and ensure that every image you're working with is small and easy to manage. That's important in IoT, and as well if you're trying to just move images around day to day. If your day-to-day workflow uses Docker, small images will make that much easier. And it lets you do so declaratively. We can do interesting complex flows, like that testing flow we looked at, without having to remember special arguments. You build it into the Docker file from day one, and then you just run Docker build, and it just works. And complex flows become well-defined within the build process itself. That's everything I've got for you today. I am Pim Terry on Twitter, and I will be putting the slides out for this in a minute, so you can go through and look through the code a little more carefully. Resin, most of the stuff we've seen here, both Balena and Resin OS, are free and open source, so you can start using them totally for yourself without Resin if you'd like to. If you do want to use Resin, it's free for up to 10 devices, so you can just get started with that. And we've actually got a booth downstairs with some demos, so you can come and have a look and play with some things if you want to see this in action. Docker is a powerful tool and lets us solve some interesting problems, but gives us some new challenges along the way. These kind of techniques and some of the things we've been building here let you solve a lot of these problems in IoT especially, and multi-stage builds really let you take that further and precisely control what's happening in your production environments to keep those images small, make it easy to work with, and keep everything secure for IoT and everywhere else. Thank you.
So, do you have any questions for Tim? Docker related, not necessarily IoT? No? I'm actually curious about something you said earlier. You can update the app independently from the OS, but how do you update the OS, or do you need to update it?
Yeah, okay. So yes, it's a good question. This is an interesting problem in IoT. You want to be able to separate the two so that you don't brick devices, but you still want to be able to update your OS. The updater has to be able to fix itself. So what we actually do for this is Docker, again, we deliver OS updates as Docker images. So we're running Docker within the OS, which is hosting a container, and then with that, we do a Docker pull, which contains a whole image that defines the whole read-only file system. And because it's read-only, we know the existing image hasn't changed. So we can just take the content out of that Docker image, write it into a new partition, and then swap. And because it's read-only, we know that's always safe. And we then swap over, and there's some migration for times when we change partition layouts and things, but that's very rare. And this allows us to separate the unstable and insecure application updates from OS updates, which we can make very, very safe.
That's very cool.
Any other questions?
No.
OK, cool. Well, I'm around, so do come and talk to me now, or we'll be in the booth downstairs. Thank you.
Thanks, Tim.